Hi, welcome back. In this video, we'll look at an advanced way views can be implemented to manage large tables. This brings us to partition views. So what is a partition view? A partition view is a view defined by a union all of the member tables structured in the same way, but stored separately as multiple tables in either the same instance of SQL Server or in multiple SQL Server instances. For now, we'll focus only on the local partition views. With partition views, we can have huge amounts of data physically separated in different tables based on the values within a specific column, and interact with these separate data sets as a unit. Imagine you have the following table. This table contains data from 2001 to the present date, and as the day-to-day business processes continue, new data is constantly being added to this table. This could easily result in millions of rows currently in the table. Having so much data stored in a single table, which is stored in one physical location, can increase the difficulty of managing it, as queries will now take longer to complete because more resources are needed to perform the requests. These long-running operations can cause locking and blocking to occur more frequently, thus degrading the overall performance. Another issue is the ability to archive data that is no longer actively used. Most of these issues can be resolved by implementing partition views. Instead of having one table that stores all the sales data, we now have 3 tables that each store a specific range of the sales data. These tables are referred to as member tables. In this example, the sales data is horizontally split based on the date column. This is achieved by making use of the check constraint. The constraint will be created on the partition key column, which is the column that determines the range of data each member table will store. This column has to be part of the primary key on each member table. We'll look at this later on in this video. One of the benefits of this design is that each table can be individually created on the same or a separate file group and can be individually managed. The first table, for example, stores the historical sales data, which encompasses the data of all sales made before 2015. The data within this table will not be subject to data manipulation and will be infrequently used for reporting. Therefore, we can put this table on a separate disk, perhaps a hard drive instead of a solid-state drive. The second table contains the data of the last 5 years and will be used frequently when generating reports. On this table, we can have a lot of strategically placed indexes for faster reporting. The last table will store the currently active data, which is heavily subject to data manipulation. This table can be placed on a faster drive, perhaps a solid-state driver to get better I/O performance. Once we have the member tables defined, we can create the partition view by simply selecting the data from each table and combining them using the union all operator. When we query the view, the data will be combined from the member tables and will be returned to the user who requested the data. Partition views can also be updatable, which means we can insert, update, and delete data through a partition view. When inserting data through the view, SQL Server needs to understand the design of the view to put the newly inserted row into the respective member table. This is accomplished with the use of the check constraint. In this example, the primary goal is not to create a view that is updatable, but to resolve some of the issues we've seen earlier with large tables. If someone were, for example, insert sales data of 2011 through the view, the data would be automatically inserted into the sales archive table because it satisfies the check constraint on that table. Subsequently, if we were to insert sales data of 2019 through the view, that data would be inserted into the second table because it satisfies the condition of the check constraint on the second table. Defining the check constraints for your member tables is a key aspect you need to take care of. If the conditions of the check constraints on the member tables overlap, you won't be able to benefit from the advantages of partition views. By having the large table split up into smaller member tables, managing the individual member tables becomes easier. As we've seen earlier, each member table can be created separately and can also be individually managed. While the primary purpose of partition views is to improve data management, you can also increase query performance. However, only if we filter the data based on the partition key, which in our case is the date column. This will allow SQL Server to perform partition or table elimination to keep the number of tables being read as small as possible. When we, for example, search for the sales data of only the current year, which is 2020, the optimizer will only look at the sales active table and will eliminate the other member tables from the query plan, because based on the check constraints, it knows beforehand that the other tables do not contain the data we're looking for. This can increase the query performance, as fewer reads have to be performed and fewer resources are needed to handle the request. If we now write a query that selects the sales data between 2017 and the present date, SQL Server will then remove the sales archive table from the query plan and only query the last two member tables. This can also increase query performance, but the increased performance will be relatively less than when we queried only the sales active table, because we're now querying two tables. Last but not least, we can have a scenario where we're querying the entire view without filtering the data accordingly. This will cause a slow-running query because we now have to read 3 individual tables. The more tables that need to be read, the more resources that will be needed to perform the request. And as a result, the query will take longer to complete. So it's good to keep in mind the importance of filtering a partition view based on the partition key. Finally, we have archiving capabilities. Data that is no longer used can be moved to another table, which can then be stored on a separate disk. Aside from partition views, we also have partition tables. Both partitioning techniques improve data management, but differ quite a lot in terms of implementation. This can make choosing a partitioning strategy quite difficult. First of all, partition views can be created on any edition of SQL Server. Partition tables, however, are an enterprise feature and can therefore only be created on the enterprise edition of SQL Server. This can be a huge factor when making your decisions. As we previously seen, the idea with partition views is that we split up huge tables into smaller member tables, which will each contain only a specific subset of the data. Each of these member tables has to be manually created either on the same file group or on a separate file group, and can be individually managed. With partition tables, we only have one huge table, which is logically split up into partitions. With newer versions of SQL Server, there are now ways to manage these partitions individually to a certain extent. Data separation in partition views is done based on the check constraints defined on the member tables. With partition tables, data separation is done based on partition function, which is then mapped through a partition scheme to the underlying file groups. Furthermore, we see that partition views can be implemented locally and can also span across multiple SQL Server instances, which is a limitation we have with partition tables. Generally, when we need to partition data locally, the preferred technique to use is table partitioning. However, there are certain use cases that justify the use of partition views. To create partition views, there are specific requirements that have to be met. For these requirements, we will head over to the online documentation for creating partition views. The conditions for creating a partition view are specified under this section. In the first part of this section, you'll find the conditions specific to the select list of each member table. Here, you'll see that all columns of the member tables have to be in the select list. Next, you have to ensure that all columns are in the same ordinal position and have the same explicit data type as well as collations. These are the same rules that apply when using the union operator. Then we have the conditions for defining the check constraints. When designing these constraints, it's important to make sure that they form a connected, non-overlapping sequence where all possibilities are covered. Next, we have the condition for the partitioning column. As stated earlier, the partitioning column, which is a column on which we define the check constraint, has to be part of the primary key. It cannot be a computed, identity, default, or a timestamp column. This definitely limits the use cases for partition views. Here we have a few specific conditions for the member tables. Very important to know here is that each table needs to have the same number of columns for the primary key. As I previously stated during the slides, partition views can be updatable, however, with the following restrictions and limitations. Last but not least, we have the additional conditions for distributed partition views, which we'll cover later on in this course. Let's head over to the demonstration and create our first partition view. Before we kick it off with this demonstration, there are a few practical things worth noting. You cannot physically split up every single table, especially tables that are being referenced by other tables using foreign keys. Since a foreign key can only reference a single table, you won't be able to implement referential integrity if you split the table up into multiple tables. Another issue might be the composition of the primary key. The primary key of the member tables is usually a composite key, comprising a candidate key and the partition key. Foreign keys cannot reference composite primary keys. Therefore, you won't be able to reference the member tables using foreign keys. This is one reason you don't see partition views frequently used on OLTP environments. These environments have normalized tables with a lot of relationships, making it relatively hard to implement partition views. So it's really important to make sure that the table you want to split up isn't being referenced by other tables. To see partition views in action, we will first create the following table. Once we have created the table, we'll execute this stored procedure to populate the table with data. I have added the code for this stored procedure as a resource for this lecture. As you can see, this stored procedure populated the non-partition table with approximately 65,000 records. These records represent orders that have been placed over the course of 14 years. This will be the table we'll split up for the partition view. The first thing we need to do is design the member tables. The first table will store the archive data, which for us will be the sales data before 2019. We can also see this in the check constraint we've defined on this table. As a requirement, this column also needs to be part of the primary key. In the non-partition version of this table, the order ID column is also an identity column. However, in the partition version, we have removed the identity property. If we leave the identity property on the order ID column, we won't be able to insert, update, or delete data through the partition view. This also counts for any default constraint we specify on the order ID column. You'll still be able to create the view, but it won't be updatable. The second table will store all the sales data of 2019, as shown in the check constraint. Finally, we have the last table, which will only store the data for 2020. Let's go ahead and create the member tables. Once we've created these tables, we can copy the data from the non-partition table to the respective member tables using the following insert statements. So, then create the partition view. The definition of this view is straightforward. We're selecting the data from the archive table, then the data from the order 2019 table, and finally, the data from the order 2020 table. We then simply combine the distinct data sets by using the union all operator. Let's execute this script to create the view. Before we query the view, we will first enable the action execution plan and the statistics I/O to see the I/O statistics of how the queries perform. The first set of queries query both the entire view and the entire non-partition table. If we head over to the execution plan, you'll notice the first query, which queries the partition view, has a slight higher query cost than the second query. The reason for this is quite simple. SQL Server had to read 3 tables to retrieve the same data. It could retrieve by just reading 1 table. This requires more resources, which is why the first query has a higher query cost. We can also see this if we head over to the Message tab. Here you can see that more read operations have been performed for the first query. This is a very ineffective way to use partition views. Let's take a look at the next set of queries. Here we are filtering the result based on the partition key. These queries will retrieve the order data for 2019. Let's execute these queries. Once they have completed, we can head over to the execution plan to see how the queries performed. As you can see, the first query has a significant lower query cost than the second query. That's because the optimizer used partition elimination to exclude tables it knows do not contain the qualifying data and therefore only queried the order 2019 table. If we head over to the Messages tab, you'll see that we have a significant reduction in the number of logical reads performed for the first query. This is what partition elimination is all about. The next set of queries perform a similar process. If we look at the execution plan, you'll notice that SQL Server now had to read 2 tables instead of 1 for the first query. That's because of the predict gates we used in the queries. Here we're selecting all the data since 2019, which also includes the data of 2020. As a result, both the order 2019 table and the order 2020 table are queried. Even though we're now accessing 2 tables, the query cost of the first query is still significantly lower than that of the second query. The third set of queries will query only the archive data. Let's go ahead and execute these queries. Once they have completed, we can head over to the execution plan to see how well they performed. This time, both queries have a query cost of 50%. This results from the uneven data distribution. The order archive table contains the largest amount of data. The more data that needs to be read, the more resource intensive the query becomes. However, the first query still performs slightly better than the second query in terms of I/O performance. Partition views aren't necessarily used for the increased query performance. They are used for simplifying data management. Because data is now stored in separate tables, each table can be individually managed. This means that we can create indexes on these tables and perhaps even alter them, as long as the conditions for the partition viewed are not violated. So next, we'll create a covering index on the order archive table to increase its query performance. Once the index is created, we can execute the previous statements again. If we now head over to the execution plan, you'll notice that our query performed slightly better. If we can even apply more optimization techniques to increase the query performance of the archived table. As I've stated during the slides, partition views can also be updatable, so we will try to insert the following row into the partition view, and hopefully SQL Server will place this row into its respective table. If we execute the insert statement, you'll see that only one physical table is affected. This is the Order 2020 table. If we now query this table separately, you'll be able to see the newly inserted row at the end of the results set. The order we inserted has an order date in the year 2020. This satisfies the check constraint of the Order 2020 table, which is why the row got inserted into the table. Subsequently, we can also perform updates and deletions, which will only affect the member tables containing the qualifying data for the DML query. In this example, we created the member tables on the same file group, which is by default the primary file group. We could have also created the tables on separate file groups, of which the data files could be stored on different disks. That's it for local partition views. In the next video, we'll cover distributed partition views. Thank you for watching. See you then.